Electrode measurements. So we have several different standard electrodes. We have the standard hydrogen electrode that has a standard reduction potential of 0 volts. We have the standard calomel electrode that has a potential of 0.241 volts. But then we also have indicator electrodes. So some of those indicator electrodes are double junction reference electrodes. They're liquid electrodes. Some of them are solid state electrodes. And we'll get into a little bit of that here in a minute. But the silver indicator electrode it is not inert. It participates in the reaction. And what happens with the silver indicator electrode is it is attached to the cathode. So what you see is the reduction of silver from the silver ion with an electrode to the silver solid. And we can use this for things like potentiometric titration. Remember that a potentiometric titration is a titration where we monitor what's happening by use of a potentiometer. And a potentiometer or a potentiometer has a positive side and it has a negative side. So the positive side is the cathode. That is where reduction takes place. And the negative side is the anode. That is where oxidation takes place. When you have something like a standard calomel electrode, it is attached to the anode. And something like our indicator electrode, in this case, the silver indicator electrode, will be attached to the cathode. So let's give an example for a potentiometric titration. Let's say we had 10.0 milliliters of a 0.0500 molar silver nitrate solution, and we're going to titrate that. We're going to watch it potentiometrically. And when we watch it potentiometrically, what we're using as our titrant is 0.0250 molar sodium bromide. So there is a response here. Now there's some information we need before we can really start calculating our titrations. So you might want to make a bullet list, you might want to make a numeric list, whatever makes you happy. But we need to point out that our anode in this case, because attached to the negative side of this cell, we're going to have the standard calomel electrode. So that means the anode standard reduction potential is 0.241 volts. The cathode for this particular cell is going to be our silver indicator electrode. So the cathode is going to be Ag plus 1 electron reacts to form Ag0. And that has a standard reduction potential of 0.799 volts. We need that information. Now we can write the titration reaction. So what we're doing is we're taking our silver ion and reacting it with our bromide anion. And that is going to form AgBr, or silver 1 bromide. And that is a solid. And you can see that on the solubility rules. That's from Chem 1. So this is what's happening in our titration. Now the KSP for AgBr, and usually when we write a KSP, we have the solid and it is reacting to form its ions. That'll be important later. But the KSP for AgBr, or silver 1 bromide, is 5.0 times 10 to the 13th. Okay, so this is the information we need. Now we can start to calculate. First thing we're going to do with our titration is we're going to figure out what our VE is, or our equivalence volume. We're going to start with the volume of our silver solution, and we're going to multiply it by the concentration, 0.0500 moles of Ag per 1 liter of Ag solution. Because everything's 1-to-1, I'm just going to kind of skip a little bit of the stoichiometry, but hopefully you can still follow along. So we have, and I'm not going to skip this part of the stoichiometry, 1 mole of silver reacts with 1 mole of bromide. So then I can use the concentration of my bromium, or my sodium bromide solution of 0.0250 moles per liter in order to find out that the VE, or the equivalence volume, is going to be 20 milliliters. Now, the part that I seem to have forgotten, because I get excited with these because I really like these calculations, is we want to find the cell potential when the volume of bromium is 0.1 milliliters 10 milliliters, 20 milliliters, and 30 milliliters. So the VE is 20 milliliters. So we're going to handle our calculations at the before the equivalence point, at the equivalence point, and after the equivalence point a little bit differently. But the potential of the cell is going to be dependent on our standard Nernstian kind of equation. E of the cell is going to be equal to the E of the cathode minus the E of the anode. But the E of the anode is static, and we know that, and that's cool. That's just the saturated calomel electrode, no problem. The E of the cathode is the tricky one. So that's going to be your standard reduction potential minus our constant divided by N, in this case N is 1, times the log log of the Q value of this reduction. So the Q value of this reduction, because we're reducing to a solid, the activity of the product is 1. And then we have the concentration of the sodium. So the concentration of the sodium is the tricky part. Now, if we are at 0.1 milliliters of bromide solution added, what is the concentration of our silver ion? Well, we have, let's find out how many moles of silver ion we have. 0.100, that's liters, times 0.0500 moles per liter, and this is our silver. So we have 0.123500 moles of silver ion in our solution. And then we're going to add some amount of our bromide solution. So that is going to be, let's see, I multiply that by 0.0250 moles per liter. And I get more zeros. And it might be better to keep this in scientific notation. Do what's best for you. Keep it in your calculator, though. But what you need to recognize is for every 1 mole of bromide added, 1 mole of silver is reacted, and we form that solid. So we're going to take these mole amounts and subtract them, and we're going to find the excess silver in our solution. And I get a value of 0.123497 moles of silver in excess. That's great. But what I have here is I have a concentration. That concentration is in molarity. So I need to take these moles of silver and divide it by the total volume in liters. And the total volume in liters at this point is 0.0101 liters. That is 10 plus 0.1 milliliters is 0.0101 liters. So when I do that, I get a concentration then. So the concentration of my silver at this point in the titration is 0.049257. It keeps going, but I'm going to leave it there. I'm just going to leave it in my calculator. So now I'm going to plug and chug. I'm going to use my E cell equation. 0.799 minus 0.05916 times the log of the reciprocal of my silver. And then I never subtracted that anode, 0.241 volts. So then I need to subtract my anode. And you should get at this particular place in the titration, you should get that the E cell is then 0.481 volts. So now we're going to take a similar approach and find out what happens at 10 milliliters because we're still before the equivalence point. So at 10 milliliters of bromide solution, how much excess silver do we have? So here I've reacted, or I have determined how many of each moles of reactant we will have. We will have 0.0005 or 5 times 10 to the negative 4 moles of silver ion. And we will have 2.5 times 10 to the negative 4 of the bromide ion. Now, because these two things react to form a solid, they're being removed from solution, and they're being removed from solution in a 1-to-1 stoichiometric ratio. So we're going to subtract these values from one another to find out our excess moles of silver. Then we're going to divide by the total volume. So the total volume at this point, we have our 10 milliliters of original sample and 10 milliliters of bromide. So we have 0.0200 liters as our total volume. That gives us a concentration of silver of 0.0125 capital M molar. That is the concentration, that looks better, of silver. So now I can use my Nernstian equation in order to find out the cell potential. All of that was to get to the cell potential. So the E of the cell is going to be equal to the E of the cathode. So we start with the standard reduction potential of the cathode, and we're going to subtract the 0.05916, our constant, times the log of the Q value. The Q value is 1 over the concentration of the silver ion. In this case, we just calculated it to be 0.0125 molar, and then we subtract the anode standard reduction potential. So the E of the cell at 10 milliliters, I get 0.445 volts. So now at the equivalence point, the concentration of the silver ion, which is really what we're after, the concentration of the silver ion is going to be dependent on how much of that silver ion comes back into solution, and we use the KSP for that. So we have some amount of solid, and it doesn't matter how much solid we have, we're at the equivalence point. So both the concentration of the silver and the bromide are going to be related to the KSP. The KSP we said up here was 5.0 times 10 to the 13th. And that's going to be equal to the concentration of the silver times the concentration of the bromide, or X squared. So what we're finding is the molar concentration. And the molar concentration at this point is going to be 7.0, and I'm actually going to leave this in my calculator, but 7.07 times 10 to the negative 7 capital M molar. Now again, what does X represent? It represents the concentration of the silver ion. So now I can use this silver ion in my Nernstian equation. The E cell is going to be equal to the E of the cathode, 799 minus 0.05916, times the log of the Q value. The Q value here is 1 over the concentration of silver minus the anode, 0.241. So you should get an E of the cell at 20 milliliters of the bromide solution being added. You should get an E of the cell of negative 0.039 volt. Nope, looking at the wrong set of data. So at the equivalence point, you should get 0.194 volts. That makes far more sense. Now we're going to 30 milliliters. Now 30 milliliters is after the equivalence point. So although we're still using the KSP equation, AgR reacts to form some amount of Ag and Br. Now we're starting with some concentration of bromine. Now that concentration of bromine is going to be dependent on the excess bromine in the solution. So the excess bromine in the solution, first we need to find out how much bromine we have. Well, at 30 milliliters, so we would calculate that as, we calculate the moles. So 0.0300 liters of a solution that is 0.0250 moles per liter. And that is 7.5 times 10 to the negative 4th. Now the moles, so this is the bromide and this is the silver. So the silver is still at 5.0 times 10 to the negative 4th moles. And because they react 1 to 1, I can just subtract these. So what I end up with is an excess of 2.5 times 10 to the negative 4 moles of Br in excess, but I need the concentration. So I need to divide that by the total volume. So I'm looking right here. And when I add those things together, I get 0.400 liters because that is the total volume in liters. And I have the concentration of the bromide ion then is 6.25 times 10 to the negative 3. So that's my initial concentration of the bromide ion. So when I go to write this equilibrium out, because I do have some solid silver 1 bromide, then that's going to decompose, and it's going to decompose in some amount X. So I'm going to be adding some amount X to both my silver and my bromide. So the KSP is going to be equal to the concentration of my silver times the concentration of my bromide, KSP value being 5.0 times 10 to the 13th, this silver being X and the bromide being represented by 6.25 times 10 to the negative 3rd plus X. Now this is one of those opportunities where you can simplify, and you can simplify because the initial concentration is more than 1,000 times different than the KSP. So as far as the KSP versus initial concentration is concerned, that X value is going to be insignificant. So we can solve this just by dividing 5.0 times 10 to the 13 divided by 6.25 times 10 to the negative 3rd. And I get an X value of 8.0 times 10 to the negative 11 capital M molar. Now that X value is equal to the concentration of the silver ion. So now I go back to my standard E cell equation. I'm looking for the E of the cathode. I start with the standard reduction potential, 0.799 volts, and I'm going to subtract 0.05916 times the log log of the Q value. In this case here, this is the equation I'm using. I'm still using the cathodic equation. See, I went and screwed that up. So I'm still using this equation for my Q value because the E of the cell is dependent on the cell, not on the solid. So I have 1 for my products, the activity of the solid, and then I have the concentration of the silver ion in the denominator. In this case, it's 8.0 times 10 to the negative 11th. So I need the reciprocal of that, take the log, multiply it by 0.05916. and subtract that value by 0.799. That's the cathode. Then I need to subtract the anode, 0.241, and now I get a total cell, E of the cell, of negative 0.039 volts. So you see, I was looking ahead when I was filling out this table. So there are, like with an acid-base titration, there are 3 different calculations you have to really pay attention to depending on where you are in a potentiometric titration. So now some reference electrodes are double junction reference electrodes. And all that means is there are 2 junctions, hence the double. So we have the first junction, which is going to be located right here. We have this, let's see if I highlight, maybe that'll be easier to see. We have this bit here. So we have 1 junction. And then here is the second junction. And what happens is we can end up forming a small potential difference there because of the two junctions. And although it's unlikely that we can measure that small junction potential, we can measure the differences in the ion concentration outside of the electrode. So this is why a pH electrode is accurate for locating pH and changes in pH, but not for the concentration of the hydrogen ion. Because we don't know what this junction is, we can't directly measure what the concentration of the hydrogen ion is. We can measure the changes in pH though. That is definitely an accurate measurement to make. But I just threw some more words out to you. So an ion selective electrode is responsive to 1 species in a solution. So it's not a redox electrode. We are looking at the differences in concentrations of a specific analyte. And that tends to occur by creating a concentration cell. So the ion selective electrode will have some sort of a hydrophobic membrane, and that will allow that selective transfer of ions to occur. And that creates what's called an ion exchange. So these electrodes work similar to the way that a cell wall in any of your body's cell membranes will transfer ions into and out of cells. And what we're measuring when we use one of these things is the electric potential difference. So we use a calibration curve in order to determine the concentration of a target analyte whenever we're using one of these things. And we usually use a modified Nernstian equation. So we have an E is going to be equal to some constant, and that constant needs to be found experimentally. So some constant, usually when it's a cation, we're adding, so plus the log of the concentration of the cations. Now, sometimes this is the concentration of the cations on the outside over the concentration of the cations on the inside. Sometimes we're adding the cations together. For purposes of keeping things as streamlined as possible and for problem solving, we're going to call this the total sum of cations with an asterisk. So that total sum of cations could be subject to what's called a selectivity coefficient. But before we get to selectivity coefficient, let's solve an easier problem. So let's look at Harris, number 1517. By how many volts will the potential of an ideal magnesium ion selective electrode change if the electrode is transferred from 1.0 times 10 to the negative fourth to 1.0 times 10 to the negative third? Well, first, let's do the first potential here. It's going to be equal to some constant that I don't know yet, plus 0.05916, the same constant we've been using so far, divided by n, the total number of electrons transferred, and that is 2, because that's how we get our 2 plus. We transfer 2 electrons. And we're going to multiply that by the log of the concentration of our analyte of interest. We're going to start with this one. And then we're also going to calculate E2. So it is again some constant. It's the same constant because it's the same electrode. And that's going to be equal to 0.05916 over 2 times the log of the analyte of interest. In this case, 1.00 times 10 to the negative third. So we set it up so that our change in potential is going to be E2 minus E1. So we go from to 2. We go from final to initial, and we end up getting, so we put like this business, and then we subtract this business. That removes the constant from the equation entirely. And then we can factor out that 0.05916 over 2, and then we end up with the log of 1.0 times 10 to the negative 3 minus the log of 1.0 times 10 to the negative 4. And if you remember your log rules, that means we are dividing those two numbers. So that is a flashback from algebra. And when you calculate all of that business, you should get a change in potential of a positive 0.02958 volts. So that is before we add the selectivity coefficient. What about that selectivity coefficient? When we have the selectivity coefficient, that is going to be added to our inert or our non-interesting ions because it does interfere a little bit. So if we use number 21 from Harris, we have a calcium ion selective electrode with a selectivity coefficient K equal to 0.010. So what the selectivity coefficient means is it is the response that the electrode has to this over the response to this. So when I say that the selectivity coefficient is 0.010, that's a decent selectivity coefficient because what I'm looking at is response to magnesium over response to calcium. Now remember, this is a calcium ion selective electrode. So the smaller the selectivity coefficient, the better the selectivity, the better the ion selective electrode is for our target analyte. So smaller K equals better. So how do I use this? Well, what would be the electrode potential if 1.0 millimolar magnesium is added to the 0.100 millimolar calcium? Well, first we need to figure out what that response is without calcium, because we have to calculate that constant. Remember, we have E is equal to some constant that we have to figure out via our experiments, plus we have our 0.05916 over N, in this case is 2, because that's how we get our charge, times the log log of the concentration of our analyte of interest. In this case, it is 0.1 millimolars. We need that in molarity, so 10 to the negative fourth. Now, again, we are still adding because we are still using cations. We'll use an anion here in a minute. So how do we go about this? Well, I can figure out what I know, and what I know is that the E is going to be equal to some constant that I don't know yet, minus 118 or 0.1183 volts. Okay, so the E with the addition of the magnesium becomes that same constant plus the 0.05916 over 2 times the log, and this is where we start adding things together and we put in that selectivity coefficient. So we start with our analyte of interest, and our analyte of interest is 10 to the minus 4 molar, plus the selectivity coefficient 0.010 times the inert ion. So in this case, that inert ion is the magnesium at 1 millimolar, so 10 to the minus 3 molar. We crunch all of those values and we get, I've realized I'm just falling off the screen. The E with the magnesium is then equal to some constant that we don't know yet, minus 0.1171 volts. So although the change isn't very large, the delta E then is going to be, we need to start with our ending. So we start with the magnesium, a negative 0.1171 volts, and we're going to subtract a negative 0.1183 volts. You have a change in voltage then of 0.0012 volts or 1.2 millivolts. Different way to say the same thing. So now let's actually calculate that constant and work with an anion. So we have two things that are going to change here. In number 19, we have a cyanide ion selective electrode that obeys the equation E equals the constant minus C. We're working with an anion, so we're going to subtract this time. Minus the 0.05916 times the log of the concentration of the cyanide. So the potential was negative 0.230 volts when the electrode is immersed in a 1.00 times 10 to the negative third molar sodium cyanide. So first, let's evaluate the constant for that equation. In order to evaluate the constant, what we need to do is insert that voltage for E and solve for the word constant. The N is 1 here. We have a charge of 1 times the log log of the concentration of the cyanide, which is going to be 1.00, 00 times 10 to the negative third capital M molar. So you should get a value for the constant is equal to a negative 0.407 volts. So now we can find the concentration of cyanide for a potential that we are given. So let's say we measure a potential of 0.300 volts. We know the constant now. We know that we have 1 electron, so we're just going to use this constant here. So now we can calculate for the concentration of cyanide. So I'm going to go through it stepwise. For those of you who may need the refresher, I'm going to add 0.407 to both sides. That gives me a positive 107 volts here. Then I have a negative 0.05916, log log of my cyanide concentration. And remember, that's our goal. That's what we're aiming for. So now I'm going to divide both sides by a negative 0.05916. And I get a negative 1.80865. It keeps going. I'm going to leave it in my calculator. And that is equal to the log log of the cyanide anion. So in order to get the cyanide concentration by itself, I need to take the antilog. That means I need to take 10 to the negative 1.808, whatever else is in my calculator. Now in my calculator, that is shift and then the log button. And I get that the concentration of the cyanide, if you want to check your own keystrokes, the concentration of the cyanide I get is 0.0155 capital M molar. So that covers a lot of the calculations, but what's with these junctions? I mean, we have liquid junctions, we have solid junctions. How do we know what's going to go where? Well, to know that, at least for the liquid junction potentials, we have what are called mobilities of ions in water. And these mobilities, if you'll notice, all of these mobilities have the same exponent. Remember, when we have a scientific notation, this part over here that I'm highlighting all the way down, that's called the exponent. And then the part that I'm going to highlight in yellow, that's called the coefficient. So if we can just look at the coefficients, we can see that like the hydrogen ion is going to be much more mobile. It's going to transfer across a membrane a lot more than, say, because it's 36.3, a lot more than, say, lithium at 4.0 or 4.01. So if we go to solve a problem like which side of the junction potential, which side of the liquid junction, that's a better way to say that, of a 0.1 molar KNO3 solution. Here's my bridge. See my bridge? And I have Na and Cl. Which side will be negative? Okay, well, let's look at those coefficients again. So the potassium, let's see if I can put this over here. The potassium mobility, I can't. The potassium mobility, I'm just going to take down the coefficient since the exponents are the same, is 7.62. Sodium is 5.19. Nitrate's mobility is 7.40, and the chloride is going to be 7.91. So the question was, which side is going to be negative? And explain your answer. Well, let's look at this. The larger the coefficient, so the larger the mobility coefficient, the more that ion will migrate. So the potassium is going to migrate this way more than the sodium is going to migrate this way. Okay, so that leads us to a positive charge over here on the right side. Now let's look at the anions. Our chloride is going to migrate to the left more than the nitrate is going to migrate to the right. Now they are close, but the chlorine is going to win out, and that's going to leave a net negative charge on the left-hand side. So that is why the left side of this liquid junction would be negative. Because the more mobility, the more the ion will move across a junction or across some sort of a semi-permeable membrane.